in this diagram 3 unit cells of a primitive cubic material are shown. For example, this is an atomic plane, as you can see, passing through the atoms here, here and here. This is also an atomic plane passing through the atoms here, here, here and here. And this plane is not an atomic plane, but it lies midway between the two atomic planes given by this as well as this. Now, the question comes, how can we name an atomic plane or a plane in the unit cell so that you can identify easily? The method that we follow in naming a plane was given by Miller, and that is the reason why the nomenclature goes by the name Miller indices. Now, let us see how the whole thing is done. So, the first step in the naming of a plane is to find out the actual intercepts which the plane makes on the x, y and z axis. Now, if we want to name this front plane here A, B, C, D, what are the intercepts this plane makes on the x, y and z axis? As you can see, the intercept is A on the x axis. However, the plane does not intersect the y axis at all, neither does it intersect the z axis. Now, if it does not intersect the y or the z axis, we can say that the intercepts made on the y and z axis are infinity. That means, the plane ABCD is such that it has an intercept of A on the x axis, infinity on the y axis and infinity on the z axis. Now, the second step is to find out the fractional intercepts. This is done by dividing the actual intercepts by the relevant lattice parameter. So, the fractional intercepts in this particular case will be A by A, infinity by A, infinity by A. The third step is to take the reciprocal of these values. So, the reciprocals will be from here it will be A by A, from here it will be A by infinity, from here it will be A by infinity, or it will be 1 0 0. Now, the next step is to put this number in a first bracket 1 0 0 within the first bracket. So, that indicates that this is this plane ABCD. So, the ABCD plane is written as the 1 0 0 within first bracket, and this is how the Miller indices are found out for this particular plane. Say for example, we want to find out about this particular plane in the simple cubic unit cell. So, this is a plane which makes the actual intercepts on x at a distance a and makes an intercept of b on the y axis and an intercept of c on the z axis. So, the actual intercepts are a, b and c on the x, y and z axis respectively. So, what are the intercepts? Fractional intercepts rather. We will divide the actual intercepts by the relevant lattice parameters. The relevant lattice parameters, say over here, are A, B and C. So, what we do? We divide the actual intercepts by A, B by B, C by C, or it becomes 1 1 1. Now, we take the reciprocal, it remains the same as 1 1 1, put these numbers within a first bracket. So, these become the Miller indices for the plane A, F and H. Now, what about this plane over here, M N H, in the cubic unit cell with lattice parameters A, B and C. Now, you see that this plane is such that it makes an intercept O n, which is half of A on the x axis. It makes an intercept O B, O H, which is equal to the B, and it makes an intercept O m, which is equal to half of C. So, the intercepts made by the plane M N H on x, y and z are A by 2, B and C by 2 respectively. Next step is to find out the fractional intercepts. So, the fractional intercepts are A by 2 by A, B by B, C by 2 by C, or half, 1 and half. What are the reciprocals? The next step, the reciprocals are 2, 1, 2. So, if we put this number within a first bracket, then it becomes the Miller indices of the plane M N H. Sometimes we may face some problem in determining the Miller indices. Say for example, in this particular unit cell, we have a plane A O B. Now, this particular plane is such that it passes through the origin at O. Now, how to name this atomic plane? It becomes difficult because it passes through the origin O. Then what we do? We take a plane parallel to the given plane AOB in the adjacent unit cell. So, this is the adjacent unit cell, and we draw a plane which is parallel. This plane is A dash, O dash, B dash, and which is parallel to the plane AOB. Now, if we look at this plane intercepts the x axis at a distance A, it intercepts the y axis at a distance minus b. This is plus b, on this side it is minus b, and it intercepts the z axis at a distance of c. So, what are the actual intercepts for the plane A dash, O dash, B dash? This A minus B, C. So, in order to get the fractional intercepts, we divide these numbers by the corresponding lattice parameters, and we get the value 1 minus 1 1. So, the reciprocals of these numbers are again 1 minus 1 1. So, the Miller indices are written by writing these numbers within first bracket. Normally, the minus sign is written on top of the number. So, it becomes 1 bar 1 1. So, this plane has got the Miller indices 1 bar 1 1. But remember, this plane is parallel to this plane. So, all planes parallel to this plane will have the same Miller indices. Then we come to naming a plane in the hexagonal system. Now, as we can see here, this is a hexagonal unit cell. As I mentioned earlier also, it is also possible to take 1/3 of the unit cell as the unit cell of the hexagonal system. So, either we can take the entire hexagonal figure as the unit cell, or take 1/3 of it as the unit cell. Say we want to name the top plane which has been shown by the blue color. Say this is the plane A, B, C, D, E, F. Now, in the hexagonal system, we have a 4 coordinate system. You see here, for example, in this plane, the lattice parameters are A1, A2 and A3, and then we have the C parameter perpendicular to this given plane. So, our job is to find out what are the Miller indices of the top plane. So, what are the actual intercepts made by this plane on these 4 axes? As it is, this particular plane will never intersect along this axis, along that axis, or along that axis, since this is parallel to the basal plane, and it intercepts the C axis at a distance c, or rather the z axis at a distance c. So, the actual intercepts made by this plane on the 4 axes are infinity, infinity, infinity and c. So, the fractional intercepts will be infinity by A1, infinity by A2, infinity by A3, c by c. Reciprocals will be A1 by infinity, A2 by infinity, A3 by infinity, c by c, or 0, 0, 0, 1. So, we can put this number within first bracket 0, 0, 0, 1, which are known as the Miller-Brave indices in case of a hexagonal system. This can also be written in this form 0, 0, dot 1. In a similar manner, in the hexagonal unit cell, if we have a plane given by I, K, E, C, we can easily find out the intercepts, the fractional intercepts and the reciprocals, and the Miller-Brave indices. The Miller indices in case of hexagonal systems are known as Miller-Brave indices are bar 1, 2, bar 1, 0, or it can also be written as bar 1, 2, dot 0. Following the same procedure, it is possible to name different planes belonging to the hexagonal system. Now, we will go to naming a crystallographic direction. In a unit cell, we can see that there can be many directions. For example, say if this is a cubic unit cell, this is a direction, this is another direction, and this is a third direction. Now, how we are going to name this direction? Say this particular direction. So, here what we are doing really, we are starting from the origin and going towards this particular point. So, how much we move from here to here? We move a distance a along x axis, and then do not move at all along y or along z. So, the numbers are 1, 0, 0. Put it in a third bracket, and that indicates this particular direction. Now, what about this particular direction here? So, we move from the origin to the point B along this direction. So, how we do that? We do not move at all along x axis. So, the total movement along x is 0. Then we move unit lattice parameter along the y axis. So, we put 1 and do not move along the z axis at all. So, again 0. So, this is the 0, 1, 0 direction. Similarly, this direction will be the 0, 0, 1 direction. Now, say we want to find out this particular direction here. given by the blue arrow. So, what should be the direction? Again, the principle is very simple. Whenever you want to find out a direction, you have to move along the x, y and z directions only in order to reach that particular point. So, our movement will be in a direction parallel to the x direction and the direction parallel to the y direction and a direction parallel to z direction. So, how we reach from this point to this point? Well, as you can see here, we have to first move along the x axis. So, we move a unit lattice parameter A along this direction, and then or simply yes, and then how much we move along the y direction? Half the lattice parameter here. So, if we move by distance A along this, we move a direction distance A by 2 along this direction and do not move at all in the z direction. So, we move by A by 2, 0 along the 3 directions. So, it becomes 1, 1 by 2 and 0, and it becomes in you can multiply by 2 to make it 2, 1, 0. So, when you put it in a third bracket, that is the 2, 1, 0 direction. So, this is normally the procedure we follow. So, whenever we want to find out any direction, we figure out what is the starting point and what is the end point, and then start moving along a direction parallel to x, parallel to y and parallel to z in order to reach that point, and that will give us the direction of the given the indices of the directions, Miller indices of that direction. Sometimes it becomes difficult to find out a direction in a unit cell. Say for example, we want to find out this particular direction here. Now, this direction belongs to this front unit cell given over here. So, this is the direction we want to find out. That means, we are moving from the point D to B. But you see, the problem is the way we find out the direction is we start from the origin. So, here we are not at the origin, but it really does not matter. You see, in a lattice, since all the points are having identical surroundings, any point in the lattice can be taken as the origin. Say for example, let us talk about the unit cell at the back of the given unit cell given by the dotted line. So, this can be considered as the origin for that unit cell. So, we draw a line parallel to the given line. So, OP is the line which is parallel to the given line OB. So, if we can find out what this direction is, it will be the same as that of the given direction. So, what is the direction of OP? How we reach the point P from the point O? How it is possible? Now, you see, if we want to do that, from the origin we move a distance minus a along x. So, the first movement will be minus a along x. Then how much we move? We move a distance a along y and do not move at all along z. So, the indices are actually minus 1, 1, 0, put it in third bracket. So, minus 1, 1, 0, it can also be written as bar 1, 1, 0. So, this is the direction given by OB in the diagram. Now, in a similar manner, it is quite possible to find out this direction or this direction. For example, if I want to find out this particular direction along OC, we know that we move unit lattice parameter along x axis, unit lattice parameter along y axis and no movement along z. So, it is a 1, 1, 0 direction. And what about this particular direction? Well, again following the same procedure from the origin, we move unit lattice parameter along this direction along x, unit lattice parameter along y, and unit lattice parameter along z to reach this point. So, this direction will be 1, 1, 1. When it comes to the hexagonal system, as I already told you, you will find we can find out the direction with respect to the entire hexagonal unit cell or the 1/3 of it, which can be taken as the unit cell. Say we want to find out this particular direction as given in the diagram. So, how we reach this point from the origin? Now, we move along x a full 1 unit lattice parameter, then half a lattice parameter along the other axis here. This is one axis, this is one axis, and this is the third axis, and we do not move along the z direction at all. So, in this particular case, we will have a situation, it will be 1, half and 0. So, make them whole numbers. So, it will be 2, 1, 0 direction. So, in this way it is also possible to find out any direction in the hexagonal system. Now, if we write a number h k l within first bracket, that indicates a particular plane. H k l are all integers. Now, as we have already seen, in a cube there are 6 similar faces, in the unit cell, the front plane, back plane, right hand side plane, left hand side plane, top plane, bottom plane, all are of the same type. So, in order to indicate similar planes or planes of the same type, we write HKL in this type of a bracket. So, this is the Miller indices of a single plane. This indicates Miller indices of planes which are all similar. Similarly, if we write a number u, v, w in the third bracket, that indicates a direction. Now, there can be similar directions in a unit cell of the same type. So, if we write u, v, w in this type of a bracket, it indicates all the directions of the same type. Now, in case of hexagonal materials, considering 4 axes, the plane, a particular plane is written as HKIL. In case of other systems, this is a 3-digit thing. In case of hexagonal, there are 4 because there are 4 axes. Now, it can be proved that H plus K is equal to minus I. So, when you find out the indices, you must make sure that H plus K should be equal to minus I. It can be proved mathematically. The other thing to remember is when it comes to a direction in a hexagonal system, we write it as U, V, T, W, and in fact we follow the same procedure as in case of naming a plane. So, U plus V must be equal to minus T. So, when we name a direction, we must make sure that it follows that kind of a procedure. Now, let us go to the different types of crystals that we normally come across. So, look at an iron crystal. In an iron crystal, it is a BCC unit cell. So, we have iron atoms at all the 8 corners and one at the body center position. Now, we know that this is a BCC unit cell, since we have along with the 8 corner atoms, one at the center. This is an FCC unit cell where we have got the 8 corner atoms and 6 atoms at the center of the 6 faces. Now, this is the unit cell of a material which has hexagonal close packed structure. You see, if it were a simple hexagonal structure, then there are these atoms on the top plane as shown and on the bottom plane. But the moment we put 3 more atoms inside, this becomes hexagonal close packed. The position of these atoms I will show later on. Now, this is a diamond crystal. So, basically again you have an FCC kind of a structure. In fact, a diamond unit cell has got 8 atoms per unit cell, which I will come to later. I will explain. Right. Now, how the atoms are packed in the different systems. Say if we talk about a BCC unit cell, in a BCC unit cell we have got the atoms at the 8 corners. So, 8 atoms at the 8 corners, and there is a central atom. Since atoms are, for a same material, atoms are of the same size, if you try to pack these atoms in this manner, you will find that all these 4 plus 4 8 corner atoms, each one of them will be touching the central atom, but between them they do not touch one another. So, in a BCC structure, we find that the central body centered atom is touched by all the 8 corner atoms, but the corner atoms between themselves, they do not touch one another. Now, when it comes to the FCC crystal structure, this is an FCC crystal structure, and I have shown here the atoms on the 1, 1, 1 plane of an FCC unit cell. Now, if you look at the way these atoms are arranged, you see they are very, very closely, most closely packed. That means atoms are touching one another in this manner. They cannot become more close, is the closest possible approach of the atoms here. Similar thing happens if we consider the 0, 0, 0, 1 plane of an hexagonal unit cell. In the hexagonal unit cell also, on this face, the 0, 0, 0, 1 face, you have a central atom which is touched by the 6 surrounding atoms. So, this is the closest kind of packing that is possible. So, in FCC material, if we look at the 1, 1, 1 planes, the atoms are most closely packed. You cannot make them any closer. Similarly, in the hexagonal system, if you look at the 0, 0, 0, 1 plane, the atoms are most closely packed. In fact, if we put a layer containing 6 atoms which touch one another and also touch a central atom here, then in order to build up the structure, we can put other atoms in these gap regions. This is one such region, this is another, this is the third, this is the fourth, this is the fifth, this is the sixth position. So, now we are trying to show how an FCC structure can be built up layer by layer, and how an HCP structure can also be built up layer by layer. Say for example, if we take a single layer as shown by the blue colored atoms, they are most closely packed. So, this is the first layer. We have a central blue colored atom surrounded by 6 neighbors, and this is the closest possible approach that can be made as in the 0001 plane of an hexagonal crystal. Now, how we build up the next layer? Either we put atoms here, here or here. This is one possibility. The other possibility is we can put atoms here, here and here. You see, we cannot put atoms at all these 6 positions because there is not enough space. The 6 atoms cannot be squeezed into those positions. So, once you fill up this position and this position and go on adding more and more atoms in that layer, you can build up a second layer. So, once we do that, this second layer, we can call it the layer B. So, the blue colored atoms at the bottom, they form the layer A and these form the layer B. Now, when you look at an hexagonal closed packed structure, as we already found out, this can be built up by putting a layer A, on top of that a layer B, on top of that again a layer A, on top of that again a layer B, on top of that again a layer A. So, this continues A B sequence. So, this gives us an HCP crystal structure. On the other hand, if we have the first layer A layer, then we have got the B layer, and then on top of that you remember that yes, if we have, instead of having atoms at these positions, if we had atoms in this and this position, that will constitute what is known as the C layer. So, if we do it in this way, that we put a layer, on top of that we put a B layer, on top of that we put a C layer, then that is the situation in FCC materials. So, the stacking of atoms in HCP will be A, B, this type, whereas in case of FCC materials, the stacking will be layer A, layer B, layer C, again layer A, layer B, layer C, like that. One thing we must remember, that the way we build up the FCC or HCP stacking, the atoms are packed most closely. That is the reason why we say that the FCC or HCP unit cells, these are very closely packed, and HCP and FCC structures are known as the most closely packed structures. On the other hand, the BCC structure is not the most closely packed. There are quite a bit of space remaining within the unit cell. So, this is a more open kind of a structure. Now, we come to compound crystals. Say for example, if we have a crystal of sodium chloride, we have got 2 different types of atoms over there, sodium atoms and chlorine atoms, or sodium ions and chlorine ions. Up till now, we have been talking about atoms of the same kind only, but now we are talking about compound crystals where we have got, say, 2 different types of atoms. So, while packing those atoms together in the unit cell, certain rules are followed. And what are those rules? The body or face centering translations, if present, must begin and end on atoms of the same kind. Now, I will tell you what it really means. as we have already seen, in case of an FCC unit cell, there are 4 atoms per unit cell located at these 4 points. So, these are the fractional indices of the 4 atoms in a unit cell of FCC material. Now, this goes by the name of phase centering translation. Phase centering translation. So, what it says, body or phase centering translation. So, in case of FCC, now in case of a BCC material, we know that there are 2 atoms per unit cell and their fractional indices are 0, 0, 0 and half, half, half. And these go by the name of body centering translation. So, the first rule is for a compound crystal, body or phase centering translations, if present, must begin and end on atoms of the same kind. I will show you by an illustration. The second rule is the sets of A and B atoms must separately possess the same symmetry elements of the crystal as a whole. So, that means, say if we take a sodium chloride crystal, as we will readily see that there are 4 sodium atoms or 4 sodium ions rather and 4 chlorine ions per unit cell of sodium chloride. Now, so there are 2 types of atoms, sodium and chlorine or A and B. So, the second rule says the sets of A and B atoms must separately possess the same symmetry elements of the crystal as a whole. That means, if you look at only the sodium atoms or only the chlorine atoms in the unit cell of sodium chloride, individually they must show the same kind of symmetry as the crystal as a whole. Now, we will see that what it really means. So, there are some examples of compound crystals. Here it is cesium chloride. So, the chlorine ion is at the center and cesium ions are at the corners of a cubic unit cell. Now, this is a sodium chloride crystal. The locations of sodium and chlorine are shown here. This is a zinc blend system or zinc sulphide. The sulfur and zinc atom, their positions are given here. Now, I will show it a little bit more detail now. Say this is sodium chloride. So, you see here the smaller atoms are the sodium atoms or ions of the sodium and the bigger ions are the chlorine as shown over here. So, if you look at only the sodium ions, for example, here this is a sodium ion, this and this, again here this, again here you can see. So, looking at the sodium ions, what we find that they have the locations as in an FCC unit cell. So, their locations are given by 0, 0, 0, half of 0, 0, half, half and half 0, half. Now, what about the chlorine atoms? The chlorine atoms have the locations given by half, half, half plus what is known as the phase centering translation. For the chlorine atoms, one atom is at half, half, half position and others can be found out by the phase centering translation. That means, the locations of the chlorine atoms will be similar to that of the sodium atoms. They have the same kind of symmetry. So, what is the phase centering translation? For sodium atoms, if one atom is at 0, 0, 0 location, the other 3 are obtained by adding half of 0 to it, 0 half to it, and half 0 half to it. In a similar manner, if we look at the location of the chlorine atoms or chlorine ions rather, it is half of half, and then we add up these to find out the locations. But you see, if you simply add up, then the locations will go outside the unit cell. The fractional coordinates will become such that they will be away from the particular unit cell we are talking about. So, phase centering translations can be positive also, can be negative also. So, what we do, these numbers we subtract from half of half, the central chlorine atom, and what are the indices, what are the fractional indices we get. If we subtract half of 0, then it becomes 0, 0, half. If we subtract 0 half from this, it becomes half, 0, 0. If we subtract half 0 half, then it becomes 0 half 0. So, you see that in a sodium chloride unit cell, there are 4 sodium ions at these 4 locations. And what about the locations of the chlorine ions? These are the 4 locations of the chlorine ions. So, the total number of ions per unit cell of sodium chloride will be 8. The sodium atoms or ions are located at these positions, whereas the chlorine ions or atoms are located at these positions. Now, when it comes to diamond and zinc blend is zinc sulphide. So far as the arrangement of the atoms in the unit cell are concerned, in diamond there are 8 atoms per unit cell, 8 carbon atoms per unit cell. And again in zinc blend also there are 8 atoms per unit cell, 4 of them are of sulfur and 4 of them are of zinc as shown over here. And what about the locations of those? Now, if we look at the diamond structure, there are a total of 8 carbon atoms per unit cell, and I will write down the locations of those atoms within the unit cell. So, in diamond there are 4 carbon atoms at 0, 0, 0, half, half, 0, 0, half, half, and half, 0, half, as in case of an FCC unit cell. And what about the others? The others are at the locations 1/4, 1/4, 1/4 plus the phase centering translation. So, what we do, add up these numbers to that one by one, and you get the locations of the all 4 atoms, the extra 4 atoms in diamond. So, there are 4 plus 4, 8 atoms, carbon atoms per unit cell of diamond. These are the locations of the 4, and the other 4 are located at this plus the phase centering translation. Now, when it comes to zinc sulphide, again the sulfur atoms are at these locations, and what about the zinc? They have got this particular location, and I have already shown you how to find out the locations by using the phase centering translation. So, in both diamond and in zinc blende we find that there are 8 atoms per unit cell. In diamond all 8 atoms are carbon atoms. In case of zinc blende 4 are sulfur, 4 are zinc atoms, and the locations have been given over here.